Welcome AP Chemistry students to Unit 4. Today we will be talking about chemical reactions, the rearrangement of atoms, as well as balancing reactions, which has a lot of practice and a lot of practical use in this course. So before we get into chemical reactions and balancing equations, we need to review physical and chemical properties. A physical property is something you can observe without changing the substance. So for example, the mass of an object, its volume, its density, its boiling point, its melting point, those are all physical properties. When you are finished with your measurements, you have the same thing you started with. Phase change is also a physical property. So if I start with ice and then I look at its phase and it becomes water, that is still water. It was either frozen or solid. It's still the same substance. Chemical properties are when atoms rearrange to give us a different substance. So for example, water, when it reacts with platinum, becomes hydrogen peroxide. A chemical property, you will often hear the words reacts with or changes into. There will be some change in the substance you're looking at. So a chemical property is how something behaves in the presence of something else, whether or not it oxidizes. So oxidation is an example of a chemical property, or if it is flammable. These would be examples of chemical properties. So when a block of wood is ground into sawdust, I start with wood, I end up with sawdust. It's still wood, however. So this is an example of a physical property. But if I take that wood and light it on fire, that's a chemical change. I started with wood, I ended with carbon dioxide and water. Water vapor is condensed into a liquid. I started with water, I end with liquid water. Those are a physical property or physical change. But if I use that water to dissolve table salt, I started with water and table salt, and I end with water and table salt. So that's also a physical property. So dissolving is a physical process. A chemical change results in a chemical reaction, where my reactants form products. Reactants will be on the left and products will be on the right. They're separated with an arrow, and you'll notice that they have some numbers to them, coefficients. Coefficients are kind of like a recipe. It takes two hydrogen molecules and one oxygen molecule to make two water molecules. So coefficients are the large numbers out in front. And we are going to talk a lot more about those coefficients at the end of this subunit. Now, when you observe a chemical reaction, you may notice some signs of a chemical reaction. So if you mix two objects together and they start to bubble or form an odor, that is a sign of a chemical reaction, or a clue that a chemical reaction might be occurring. So the formation of a gas is a sign of a chemical reaction. If you take two solutions and mix them together and they become cloudy, that could be the formation of a precipitate. So in the example here, where lead nitrate and potassium iodide are mixed, they make this cloudy substance, lead iodide. That is an insoluble precipitate that comes out, a sign of a chemical reaction. If there's a change in temperature, that's a sign of a chemical reaction. Or if there's production of light, that's another sign of a chemical reaction. So when you strike a match, the phosphorus at the end of the match, that red powder substance, is given just enough energy to begin reacting with the air around it and produces a flame, which shows a change in temperature and also produces light. Two signs that this is a chemical reaction. And lastly, if there's a change in color, specifically a loss of luster, metals will react with the oxygen in the air to make oxides or rust. So this iron nail will become iron oxide. It rusts in the presence of air. All five of these are signs that a chemical reaction could be occurring. Not all five have to occur simultaneously, but you can see them as a clue that perhaps a chemical reaction is occurring. So in your packet, we did this worksheet from first year chem where we separated chemical and physical properties. If it's a physical property, it can be further classified into whether it is intensive or extensive. Intensive physical properties are independent of how much you have, meaning a cup of water and a glass of water might be at the same temperature. A cup of water and a glass of water would have the same density. So intensive physical properties are the same whether you have a lot or a little. So in the first example, a solid cube, states of matter are physical properties, and it doesn't matter whether you have a cup of water or a glass of water, they would both be the state of matter. So that is an intensive physical property. Physical properties can also be broken down into whether or not they are a number, a quantity, or a opinion, a quality. So solid would not be a number, so solid is a qualitative physical intensive property. Extensive physical properties change depending on how much you have. So a cup of water and a glass of water would have different volumes. A cup of water and a glass of water would be different masses. So extensive physical properties change based on the amount you have. So in the first example, 38.1 grams. 38.1 grams. Grams is a physical property because I can measure it without changing the substance. It is extensive and is a number. So it's a quantitative, extensive physical property. For an example of a chemical property, chemical properties change what you're looking at, or is how something reacts with something else. So in the first example here, reacts with an acid or a base, that is a chemical property. Reacts with is one of the clear signs there. So look for words that sound like you're changing the substance. If it oxidizes, if it's flammable, all right? Those would be chemical properties. Go ahead and pause the video and complete page 14 in your Unit 4 packet. We also broke down substances based on representing them in a particle sketch. A particle sketch uses circles of different colors, different shades, or different shapes to represent different substances. So if you see a particle sketch of all one shape or one color, this would represent atoms of a particular element. Since these are all the same, this is elemental atoms. But if you see atoms held together, they form molecules. So here we see molecules of water, which is a compound. Compounds are two or more elements held together. The example here shows oxygen gas, which is molecules, because I have two atoms held together, that are the same. So this is a molecule of an element. So when you have just one substance, so we have just one type of atom present, one element, those are elemental. Compounds are when you have two or more different elements bound together. Lastly, a pure substance is when the only one thing is present in your picture. So this is a pure substance of an element that exists as atoms. A mixture is when you see two or more things present in your picture. So here I have a mixture of molecules. One is an element and one is a compound. So for example 2, we are asked to classify each picture as atoms or molecules, elements or compounds, and a mixture or pure substance. So for the first one, all of these circles are the same. So these are all elements. But none of them exist alone, so they are molecules of an element. And there are two different things here. If these were oxygen, so this must be oxygen, this could be ozone. This is a mixture of elemental molecules. Example B, we've got some atoms that exist alone, so they are elements. We also have some molecules that are compounds. So this is everything. These are atoms, a mixture of elemental atoms and molecular compounds. Lastly, we see the atoms by themselves and they form elements. And since there's nothing else present, this is a pure substance of elemental atoms. So in your packet on page 15, I ask you to break down the images. All cards on the table, these examples were lifted from that page, so you already, of the 6, have 3 done. Please do the 3 that we did not do. Pause the video and complete page 15. Particle sketches actually can be used to balance reactions, so understanding what a chemical reaction shows might help you understand what we will be doing later. So for this example, I'm asking you to draw particle sketches of the Haber process when hydrogen and nitrogen form ammonia. So hydrogen is an elemental molecule, so we might show it as such. 2 circles touching, 2 exact same circles. Since there are 9 hydrogen molecules in this equation, I'll just draw them. Notice that I drew them spread out in my particle sketch. That's because hydrogen is a gas. So I separated them to show that they are not held together in a solid. Nitrogen is also diatomic, and our equation showed 3 nitrogens come together with our 9 hydrogens. Again, nitrogen is a gas, so I would show it as such. If I wanted to show a solid, I might show them all very closely packed together, like this is gold. Gold is a solid at room temperature, so notice that these molecules are very closely packed together. Gases, you would show spread apart. Lastly, these come together to form 6 ammonias. Ammonia is a gas, so why don't you pause the video and see if you can complete a particle sketch for what the 6 ammonias might look like. Hopefully you have 6 nitrogen atoms with 3 hydrogens attached to each of them, showing your 6 ammonias. If you are really on top of things, you might remember that ammonia is a trigonal pyramid, so you showed your 3 hydrogens on one side. If you didn't, that's not the end of the world. In particle sketches, it's not necessarily required that you show correct VSEPR models, but in the interest of being a good teacher, I've showed you the best I could. Now this particle sketch shows a balanced reaction. Balanced reactions show the conservation of mass, that matter can be neither created or destroyed. So if I start with 2 hydrogens and 2 oxygens, I have to end with 2 hydrogens and 2 oxygens. The example here, hydrogen and oxygen make water, is not balanced. Where did the other oxygen go? It wouldn't have formed an oxygen-free radical because you're smart, you're pretty, gosh darn it, people like you, you know that oxygen is one of the 7 elements that can never exist by itself. It's always in something, or if it ever is alone, it's diatomic. So there's no such thing, or at least not at this level, of an oxygen-free radical. This would not be this would not be a acceptable answer if I ask you to balance an equation. Another no-no would be if you changed it so that you kept those 2 oxygens. But this is no longer producing life-sustaining water. You are producing vomit-inducing hydrogen peroxide. So that is also not a viable way to balance a reaction. The only way to balance a chemical reaction is to use coefficients. If I need to end up with 2 oxygens, if I put a 2 in front of water, that tells me I have 2 oxygens and 4 hydrogens. So for every oxygen, it must take 2 hydrogen molecules to balance it out. So balancing, we are going to use coefficients to balance them. In our previous example, you see that all 6 of our nitrogens get paired up with 3 hydrogens. So to make that work, it would take 9 hydrogen molecules for all 3 of our nitrogen molecules. This is a balanced chemical reaction. So again, we balance chemical reactions by adding coefficients. Coefficients apply to the entire molecule, while subscripts only apply to the atoms directly in front of them. Now, there are many ways to do balancing. Personally, I do atom inventories, so that is what I'm going to show you. However, you could just as easily do particle sketches. This shows a balanced reaction. In reality, you want the lowest coefficients possible. So 9 to 3 to 6, that is not the simplest ratio. I could pull a 3 out of here, giving me 3 to 1 to 2. That would be a balanced equation. So if this was a 3, a 1, and a 2, this would show the balanced reaction, and we could have gotten it by drawing just this. Our 3 hydrogens with 1 nitrogen made 2 ammonias. Again, personally, I do not prefer particle sketches. When I balance, I use an atom inventory, where I need to get the numbers on the left to equal the numbers on the right. So as long as 1 carbon becomes 1 carbon and 4 hydrogens become 4 hydrogens, the reaction is balanced. So this is the method I'm going to show you. Please realize that instead of numbers, you can just as easily draw pictures and end up with the same answers. Lastly, before we get to the examples and continuing on, balancing is a skill. It is something that you will get better at the more you practice. So at the end of this little subunit, you will have lots of practicing. And if balancing continues to elude you, I highly suggest you practice this. The internet is a wonderful place sometimes, and you can find lots of examples of balancing, and you can get lots of practice. So I strongly advise you, if balancing is not your friend, to get better at it, because it is the cornerstone of chemistry. The law of conservation of mass will always be observed, so you must learn to balance chemical reactions, or the rest of the year will be nigh impossible. Now, as with all skills, as a former coach, I could teach children how to spike a volleyball, how to serve over the net overhanded. That was my job. I could teach that skill. However, when it came to properly executing it, all I could do was give you tips. So when it came to hitting the volleyball, I could tell you, start your approach as the ball is descending. That's something you had to learn to do on your own. So when it comes to balancing, practice is your best bet to get better at it. I can give you some tips that I've learned over the course of my time, but it's not going to save you from everything. So when it comes to balancing, my first tip is, if you see polyatomic ions, always keep your polyatomic ions together. Here we have sulfuric acid and barium nitrate coming together to form the insoluble barium sulfate and nitric acid. Sulfate and nitrate are polyatomic ions. So rather than balance 1 sulfur and 1 sulfur and 2 nitrogens and 1 nitrogen, I'm going to treat them as their own entities. So when I do my atom inventory, I have 2 hydrogens and 1 sulfate ion. I've got 1 barium and 2 nitrate ions. Again, I'm going to treat them as their own entity. And as long as they're the same on both sides, as long as my sulfate stays sulfate and my nitrate stays nitrate, this will save me a lot of headache. So on the product side, I end up with 1 hydrogen, 1 sulfate, 1 barium, and 1 nitrate. Obviously, this is not balanced. 2 hydrogens cannot just disappear into 1 hydrogen. So I can balance this by putting a coefficient in front of the molecule I find hydrogen in. Hydrogen exists exclusively in this nitric acid in the product side. So if I put a 2 as the coefficient, that changes this 1 to a 2. I now have 2 hydrogens, but it also affects the nitrate. I have 2 nitrates. And that by itself balances this reaction. So my coefficients would be 1 to 1 to 1 to 2. If there's no number there, obviously there is a 1. So this reaction is balanced now. My next trick, or my next advice for you, is to save anything that's elemental for last. Here we see the combustion of methane, where carbon and hydrogen react with oxygen to form 1 or more oxides. Doing our atom inventory, 1 carbon becomes 1 carbon, and 4 hydrogens become only 2 hydrogens. Oxygen, we start with 2 oxygens, we end with 2 plus 1 for a total of 3. If something is in multiple places, I suggest you keep it separated. You can keep a running sum, but you will want to observe them different, because putting a coefficient here is going to affect only one of those values. All right. Since oxygen is elemental, I will do oxygen last. So let's start with carbon. 1 carbon becomes 1 carbon. That is balanced, but 4 hydrogens cannot become 2 hydrogens. So I need to put a 2 in front of the molecule where I find hydrogen to give me 4 hydrogens. But that 2, while increasing the number of hydrogens, also increases the number of oxygens. 2 times 1 is 2. So I now have 4 oxygens as a product.
So I just need a 2 in front of elemental oxygen.
If you ever get in trouble, my final tip is to double everything except for what's giving you a hard time. So here we see a combustion reaction again, where something reacts with oxygen to produce 1 or more oxides. And once we get our atom inventory, we see that everybody is all over the place. We will save oxygen for last since it is elemental and start with carbon. 2 carbons cannot mysteriously disappear into 1 carbon, so I need to put a 2 in front of the molecule I find, carbon, to give me 2 times 1, or 2 carbons, but that also applies to the oxygen, so 2 times 2 is 4. We're going to save oxygen for last, so I'm not going to keep going with that. Let's talk about the hydrogen. 6 hydrogens cannot disappear down into 2 hydrogens, so if I put a 3 here, that'll give me 6 hydrogens, but that will also change my number of oxygens. I now have 3 oxygens from that water, plus 4 from the carbon dioxide. In order to balance this reaction, I need to put a coefficient here that when multiplied by 2 gives me 7. But there's a problem. You always balance with whole numbers. So nothing times 2 gives me 7. 7's not a factor of 2. So you're stuck. What are you supposed to do? Well, if you ever are stuck, double everything except for what's giving you a hard time. So I'm going to come back through and double all the numbers I have here so far. And then re-evaluate where you're at. 2 times 2 is 4. 2 times 6 is 12. I'm going to leave this blank for right now, 2 oxygens. 4 times 1 is 4. 4 times 2 is 8. 6 times 2 is 12. 6 times 1 is 6. That gives me 14 oxygens in the product from the 2 oxygens in the reactant. So if I put a 7 in front of the molecule containing oxygen, that'll give me the 14 oxygens in the reactants. Some other good tips or some other good things to memorize is that a metal plus a halogen will always make a metal halide, where the subscripts, where it's always one cation of the metal to some number of the halide, where that's the oxidation state of the halogen. If something reacts with oxygen to produce one or more oxides, that's known as a combustion reaction and is a very common reaction. There is no such thing as carbonic acid. Carbonic acid instantly decomposes into carbon dioxide and water. So if you ever have a product of a reaction where you think it's carbonic acid, that's not a thing. It always makes carbon dioxide and water. Metal carbonates will almost instantly break down into metal oxides when heated. So metal carbonates, so for example, magnesium carbonate, when heated, will break down into magnesium oxide and carbon dioxide. We can also write chemical equations from word problems. For this, you really need to remember your nomenclature and to keep an eye out for those diatomic elements. It says sulfur trioxide is produced from the incomplete combustion of sulfur of fossil fuels. It reacts with water vapor to produce hydrogen sulfate, a key component in acid rain. Write the balanced chemical reaction for this process. Sulfur trioxide is a covalent compound. The prefix tri tells us that it's sulfur with 3 oxygens. It reacts with water vapor in the air. Water vapor is water that is a gas, to produce hydrogen sulfate. Sulfate is SO4 with 2 extra electrons, and hydrogen is a group 1 metal, so that would be H2SO4. And since it's a key component of acid rain, this is probably a gas as well. In fact, this whole reaction probably takes place in the gas phase. So if you're ever asked about the states of matter, we show states of matter with a little g for gas, L for liquids, and S for solids. You know what state of matter something is by looking for some keywords. Gas or vapor obviously is a gas. Liquids are pure liquids, so something that exists as a liquid at room temperature, and it says it's a pure substance, so this water would be a liquid, but since it says it's a vapor, it's a gas. And solids, it will either say it's solid or it will say some sort of shape, like filament. Those are shape words, so that tells me it's a solid. Now, in terms of is this reaction balanced, I've got 1 sulfur, I've got 3 plus 1, or 4 oxygens, and I've got 2 hydrogens. That becomes 1 sulfur, 4 oxygens, and 2 hydrogens. This reaction was balanced just based off of the nomenclature. I don't have to do anything. Its coefficients are 1 to 1 to 1. When solid ammonium dichromate is ignited, an interesting reaction occurs. Although the reaction is somewhat more complex, let's assume the products are chromium oxide, nitrogen gas, and water vapor balance this reaction. So ammonium dichromate, when heated, produces chromium 3 oxide. That 3 tells us that chromium must have a +3 oxidation state. Oxygen oxide is always a -2, so it would take 2 chromiums for every 3 oxides. It also produces nitrogen gas and water vapor. We're asked to balance this reaction, so I'll set up my atom inventory. We do not have the same polyatomic ions on both sides, so my first tip doesn't get you through this. You need to look at each element. 2 nitrogens and 8 hydrogens, 2 chromiums and 7 oxygens. We end up with 2 nitrogens, 2 hydrogens, 2 chromiums, and 3 plus 1, or 4 oxygens. Obviously, this reaction is unbalanced, so we can go ahead and start balancing it. The nitrogens are fine, but our hydrogens are a little wonky. So in order to balance our hydrogens, we would need to put a 4 in front of the molecule we find hydrogen in. 2 times 4 will give us the 8 hydrogens we started with, but it's now going to also offset our oxygens. 4 times 1 ends up giving us 4 oxygens in water. Looking on to chromium, 2 chromiums becomes 2 chromiums, and we started with 7 oxygens, and that 4 gives us the 7 oxygens. So this is balanced with the coefficients 1, 1, 1, 4. Example 8 says ammonium gas reacts with oxygen to form nitric oxide and water vapor. Balance this reaction. So ammonium and oxygen form nitric oxide and water vapor. To balance this reaction, we set up our atom inventory. One nitrogen becoming 1 nitrogen is fine, but 3 hydrogens and 2 hydrogens are not balanced. Now, nothing times 2 gives me 3, and nothing times 3 gives me 2, but they could both get to 6. So if I put a 2 in front of ammonia and a 3 in front of water, that'll give me 6 hydrogens in each one, but it's going to throw some of these others off. I now have 2 nitrogens in the reactants and 4 oxygens in the products. So this is still not balanced, and now that my nitrogen's thrown off, I can go back. 2 nitrogens cannot disappear down to 1 nitrogen, so I need to put a 2 in front of the molecule with nitrogen, giving me 2 nitrogens, becoming 2 nitrogens, but it's going to offset my oxygens. With nitrogen and hydrogen balanced, 2 oxygens cannot mysteriously become 5, and again, I'm in a bit of a pickle. Nothing times 2 gives me 5, so I am stuck. Remember, anytime you're stuck, you need to double everything except for what's giving you a problem. Since oxygen is challenging me in the reactant side, I'm going to leave oxygen blank. I'm going to double everybody else. 4 ammonias, 4 nitric oxides, and 6 oxygens, and then reevaluate everybody. So 4 times 1 is 4 nitrogens, 4 times 3 is 12 hydrogens. I still have just 2 oxygens. 4 times 1 is 4 nitrogens, 4 times 1 is 4. 6 times 2 is 12 hydrogens, 6 times 1 is 6, so I end up with 10 oxygens in the product. So if I put a 5 here, this will give me the 10 oxygens I start with. So our coefficients are 4, 5, 4, 6, and that is the simplest ratio because I can't pull any numbers out. So when you balance, they got to be whole numbers, and they got to be the simplest ratio. As I said, you have lots of practice ahead of you. So on page 16, please balance all of the problems. Remember to keep your polyatomics together, right? So phosphate here becomes phosphate there. Don't try to balance phosphorus and oxygen separately. Just be like, I have one phosphate, and don't put the oxygen in with the other. Another little side note, guys, water is 2 hydrogens and an oxygen. So you could rethink water, especially if you have hydroxide as a reactant, as HOH, because that's where your hydroxide ends up. But that's just a tip, just a little hint, a little thing to get you through. No matter what though, please practice balancing, and if you are mystified, if you get to the last one and still are struggling, having to look things up, I suggest you go online and look for more practice, because you absolutely must know how to balance in order to do net ionic equations and later stoichiometry. I will see you all next time for net ionic equations.